Good morning, class. So let's now discuss sets and set operations, so which is one of the basic concepts in mathematics. So we know that a set is a collection of well-defined objects. For example, we say set A is a set of flowers, so the elements are would include gumamela, sampagita, rose. So a banana cannot be a part of the set because a banana is not a flower. A set can be denoted by letters, capital letters A, B, for example, or by letters with subscripts. So we have here A sub 1, A sub 2, and A sub 3. So a set can also be denoted by those. Now, the objects that a set contains are called its elements. And the notation A is an element of A, so small a is an element of capital A, means that A is an element of set A. Whereas this notation, so there is a bar across this symbol, means that A is not an element of set A. Like what I mentioned earlier, where we had a set of flowers and we had rose, gumamela, and sampagita as elements. So the three are elements of that set, for example, set A, and banana is not an element of the set. So that's what this symbol means. So for example, we have here a set which contains the numbers 1, 2, 3, 4, 5. We say 3 is an element of set A because 3 is contained in the set A, whereas 6 is not an element A because obviously 6 is not part of the set. Now, a set can be described by putting its elements in curly brackets or braces, like this one. So these are braces. So we have here the set whose elements are the integers 1, 2, 3. Now, a set can be described also by giving a logical conditions. Imagine if we are to write a set which includes all the students of CBSU Carmona, and there are more than 2,000 students, no, for this semester. So we will be listing 2,000 names, and that would be tedious, no. So there must be another method of writing a set which would not require us to write all these elements, okay? And so we call that the set builder notation. So we just write the characteristics. We mentioned earlier that a set is a collection of well-defined objects. So P of X will give us the definition of the set. So for example, we have the set A which contains the numbers 1, 2, 3. In set builder notation, we can write this as X, where X is a natural number less than 4. Okay? So even though if we will have many elements of the set A, if we use this notation, we will not have difficulty. Now, a set is determined by its elements, no? So just like any mathematical operations, a set is also binary. So we can compare two sets and determine their equality or their equivalency, no? So suppose we have two sets A and B. Sets A and B are equal sets if and only if they have the same elements. So the elements are identical. Even if they are presented differently, as long as the elements are identical, then the two sets are said to be equal sets. Again, the elements need not be shown similarly. For example, 1 is 1, 2 is 2. So we could write elements of B as 2, 3, 1, 4. But as long as the elements are identical, the two sets are said to be equal sets. Now, two sets A and B are equivalent if they have the same cardinality. Okay? So the absolute value of A is equal to the absolute value of B. So this is written this way, but it means the cardinality. The cardinality refers to the number of the sets. How many elements are in the set? If two sets, for example, A and B, possess the same number of elements, then they are said to be equivalent. So set A has the elements 1, 2, 3, whereas set B has the elements 3, 6, 7. So if you count them, they have the same cardinality, which is 3, and therefore we say set A and set B are equivalent sets. Now, since we mentioned earlier that equal sets have identical elements, so, it is sufficient to say that equal sets are equivalent sets. Since the elements are identical, they must have the same, the set rather must have the same cardinality. No? Elements, they are the two sets which are equal have the same number of elements. And therefore, equal sets are also equivalent sets. But we cannot say the converse, no? Not all equivalent sets are equal sets, okay? So in fact, two sets which are equivalent need not be equal sets. No, as long as they have the same number of elements, meaning they have the same cardinality, two sets are said to be equivalent. So equality of sets is more strict than equivalency. Again, all sets which are equal are equivalent, but we cannot say the converse. Okay, now since sets are determined by their elements, there is a unique set which we call this symbol phi, which has no elements. No? And therefore, this set is what we call the empty set or the null set. And a set is called to be finite if its elements can be listed, meaning the cardinality can be determined. For example, we have set A with elements 1, 2, 3, up to n element. So we can count the number of elements. So there are n elements, and therefore the set A is a finite set. If we cannot determine the cardinality, then that set is called to be an infinite set, like the set of natural numbers, because we do not know when the element would end. No, what is the last element, I should say. No, we do not know when n would stop, so set n is an infinite set. Now suppose we have two sets A and B. So we say B is a subset of A if each element of B is an element of A, meaning all elements of B can be found in the set A. Then we say B is a subset of A. For example, we have the infinite set A, which contains the elements 1, 2, 3, and so on. So set B containing the elements 1, 3, 6, 9, 15 is a subset of A. In fact, it's a proper subset. Okay. Now, if a set A, okay, suppose we have the set A here, and we describe the set of all subsets of A, now that resulting set is called the power set of A. So a power set of a set is a set which contains all the subsets of the defined set. For example, we have the set A, which contains the elements 1, 2. Now we are asked to describe the power set of A, so we just list all the elements of P of A which are actually the subsets of A. So we include the null set or the empty set, which is always a subset of any set. Then we include the element, the set rather, which contains the element 1, the element 2, and then the given set A itself. So a set is always a subset of itself. So here we have 4 elements, so there are 4 subsets of this set. So the empty set, this set which contains the element 1, the set which contains the element 2, and the last subset which contains all the elements of the given set. So this is the power set of the given set. Now, if A and B are sets, and then we are asked to find the product set or the cross product of sets A cross B, then that is just the set which contains all the ordered pair AB, where A is an element of A and B is an element of B. So in a set builder notation, we denote it this way. So A cross B is the ordered pair. So there are 2 numbers, there are 2 elements, no? The first number and then the second number B. A is an element of the original set A, whereas B is an element of the original set B. I repeat, A is an element of A and B is an element of B. So suppose we have the sets 1, 3 and the set B which contains the elements 2B. So A cross B must be the set which contains the ordered pair. So we take 1, pair that with 2. So that's the first ordered pair. We take the element 1 and pair that with 5, which is an element of B. Then we have the ordered pair 1, 5. We take the element 3 and pair that with 2. So we have the ordered pair 3, 2. And finally, we take the element 3, pair that with the element 5. So we have 3, 5, which cannot be seen because it's covered. So we have the ordered pairs 1, 2, 1, 5, 3, 2, and 3, 5. So that's the cross product. So the first set which appears should have, the ordered pair rather, of the cross product should have the elements of the first set as the first entry. What about the union of two subsets? No? So if we have the set X, where sets A and B are subsets of the set X, the union of the two sets A and B is the set which contains the element X element of the set X, where the small x is an element of the set A, or small x is an element of the set B. Okay? So suppose we have the set A rather, which contains the elements 1, 3, 5, and the set B, which contains the elements 2, 4, 6. The union of sets A and B is the set which contains everything. No? So we want the elements of A or the elements of B. Therefore, that would mean all the elements, no, of A and elements of B. So we just list all the elements. Now, if it happens that an element of A is also an element of B, we need to write that once only. Okay. What about the intersection of two subsets? Again, we have the set X, where sets A and B are subsets of the set X. The intersection of the sets A and B is the set which contains the elements X, element of capital X, where this time X is an element of A and X is also an element of B. Unlike in the union where it's or a disjunction, this one is a conjunction. The elements must both be elements of the two subsets A and B. For example, we have the set A which contains the elements 1, 3, 5, the set B which contains the elements 2, 4, 6, and the set C which contains the elements 1, 2, 3. The intersection of the sets A and C, so you look at the elements of sets A and C. So what are common to the two sets? So obviously 1 and 3 are common. So the intersection of sets A and C is a set which contains the elements 1, 3. Why? Because both elements can be found in the two sets. The intersection of the sets B and C. So again, you look at the elements of B and you look at the elements of set C, and notice that 2 is common to both sets, and therefore the intersection of the two sets B and C is a set which contains the element 2. What about the sets A and B? What is the intersection of the two sets? If you look at set A, so the elements are 1, 3, 5, and you look at set B, the elements are 2, 4, 6, it is easy to see that there is no common element to both sets A and B, and therefore the intersection is the null set, no? The null set or the empty set. So it is a set which contains no element. Why? Because there is no common element to both sets A and B, and therefore A and B are called disjoint sets. So if two sets have no elements in common, they are called disjoint sets. What about the difference of two subsets, A and B? No? So the difference of the sets A and B is the set which contains small x, which is an element of the capital set X. So we define the element X rather as an element of A but not an element of B. Okay, so that's the difference. So for example, we have the set A which contains the elements 1, 3, 5, 6, and set B which contains the elements 1, 2, 3, 4. So what is the difference of the two subsets? So A minus B. So this is the set which contains the element of A which is not found in B. So if you notice, 1 and 3 are both elements of sets A and B, and therefore this is not part of A minus B anymore. So we just include the elements of A, which are 5 and 6, which are not an element of set B. So that's A minus B. What about the complement of a set? So this is different from the complement. No, complement with a letter I. For example, you say somebody is you see a friend who's wearing a nice shirt, for example, and you would probably say to your friend, "Oh, you're wearing a nice shirt." So that's a complement. Complement. PLI. So we have here a complement, a complement. So what's a complement of a subset? So a complement which we denote by E superscript C or A apostrophe A, no, A apostrophe rather, is the set which contains the element X, which is the element of the set X, which is not an element of A. Okay, so for example, we have the set X with elements 1, 2, 3, 4, 5. And we have the set A with the elements 1, 3, 5. So the complement of A are elements of X which are not in A. And obviously, those are the elements 2 and 4. Okay, it's it's like it's easy to remember the complement if you think of a relationship, for example. If you look for your significant other, you would find you need to find your complement, no? Because your weakness is the strength of that person, and your weakness is the strength of that person. I don't believe in compatibility, no? But we would hear people, "Oh, you're very compatible, you must make a great couple." I think that it's better for us to be uh, having a relationship with our complement. For example, I am a good cook. The significant other must be someone who has a good appetite. Imagine if I cook all the time and my significant other also loves to cook. Who would eat the food? No? So it's better to find our complement. So if you are a good talker, find somebody who's a good listener. That way, you will have a very nice relationship. So that's the complement. So here we have a Venn diagram, which is a diagram, no? A figure which shows relationships between and among sets, no? So the union of sets A and B can be shown, no, here. So the union of sets A and B here is depicted by the yellow color. So what's the union? So it's the set which contains the elements of A or the elements of B. Suffice to say, we just combine all the elements of sets A and B. So here, the difference of sets A and B, specifically A minus B. So the set A minus, so we get rid of the set B. So what is left is the blue portion. So notice that part of set A is overshadowed by set B. So this is not part anymore, no? Though this portion is still part of set A, but is also a part of set B, and we do not want B, therefore the blue portion is the answer to A minus B. And we have the intersection of sets A and B. So what's the intersection again? So it's a set which contains element found in both sets. So this is the representation of the intersection of sets A and B. using Venn diagram. So this shaded portion, all of the points here are part of the set of intersection between sets A and B. And finally, complement. So it's part of the universal set, but not part of set A. So the whole thing, the rectangle is the universal set, and this circle represents the set A. So we want the complement of A. So these are the elements of the universal set which are not found in A. So all of these shaded portion. So that's it for our sets and set operation. So the next slides would allow you to have an exercise on sets, operations, and sets rather, and Venn diagram, which you need to do on your own. Thank you.